Good morning. My last class of the day yesterday was like, yeah, sure, you should totally wear an Olaf costume. So here's what I got. Put this on, right? Oh dear. This thing is actually very warm. All right, let's double check on volumes here. Yeah, that's working. Okay, cool. I'll move this there. I can barely see. All right. Good morning. Last day of class, so I thought, why not dress up in a fun costume? Here's a warm up. I'd like to talk through this because today's topic, while it is new, it's not really too bad. I think among the topics we could be ending a semester on, at least it's not optimization or something like this. Today you'll find, I hope, to be a good review of differentiation. It's been a while since we've been doing the reverse of differentiation. Now I got this function, f of x equals 3 times x to the fifth times 100 plus 100 ln of x plus 10 to the x power. And the question is to find the derivative. We've been so used to maybe anti-differentiating, we've got to be careful of like when is it time to differentiate, when is it time to anti-differentiate. Excuse me. And here's the thing, before differentiating, if you really want to, you can take the 3 here and the 100, multiply them together to have 300. So you'd really have 300 times x to the fifth. And of course, if you have a constant times a function, you copy the constant. So this 300 still copied, although it is written a little funny, as the 3 and the 100 are still separated. But that's fine. The point is, if you have several constants multiplied together times a function to differentiate, you copy each of the constants, and I copy them each in place, even though I could have shuffled them. And then this x to the fifth was differentiated to a 5x to the fourth. Same deal here, right? There's a constant 10 times a function ln of x, so the 10 is copied, but the derivative of ln of x is 1 over x, and then the derivative of 10 to the x is 10 to the x times ln of 10. So good reminder here, because it's been a while, of the derivative of exponential functions. You might find it a little bizarre. Why not just do 3 times 100 first, simplify that, and then say that the derivative here is 300 times 5x to the fourth? But it's mainly just because of something we're going to do with this. We're going to relate back to this warm-up as an example later in class today. So that's really the only reason. Okay, so yeah, This comment is here. Just I think I kind of spoke through it, but just as a reminder here that for the first term, 3 times x to the fifth times 100, it is a product, but you don't have to use the product rule because 2 of the 3 pieces are constants. So we applied the constant multiple rule and differentiated just the x to the fifth part using the power rule. Just to make sure this comment is making sense, we've been doing things like this ever since we started derivatives, but I just want to really make sure that I'm clear by this idea of the constant multiple rule is applied and the instead of the product rule. So I have a smaller example. I think often when we differentiate 10x to the fourth, we think, oh yeah, we're just going to take 10x to the fourth, apply the derivative. We just kind of very directly we multiply in our heads 10 times 4 right away and just say that the derivative is 40x to the third. There's nothing wrong with that. That is true. But we are technically skipping a step here. And I think for the purpose of what we're doing today, it's helpful to know that a step is being skipped. We might not even notice that the constant multiple rule is being used. So I actually would prefer for a moment to take this smaller example, the derivative of 10x to the fourth, and really just take it step by step. Right now, it's just to say, hey, this really is, if we're being asked to differentiate, that's what that prime is, then this really is 10 times x to the fourth, take its derivative, and this, when you differentiate, and there's one of the pieces is a constant, you can copy the constant and then differentiate the function. So just to really do it one step at a time, the part going from here to here is showing of the constant multiple rule at work, right? There we go. So that we've got let's see, so derivative of 10x to the fourth is 10 times the derivative of x to the fourth. That's the constant multiple rule. And then, sorry, this costume is like, it's incredible. I think I'll see how long I can. Oh my goodness, I'm sweating. Okay, and then copy the 10, and the derivative of x to the fourth using the power rule is 4x to the third, right? So one step at a time. The first equals is about the use of the constant multiple rule. The second equals here is about the use of the power rule. Today we have one new idea, but the basic goal of today is it's an excuse to review derivative rules. Just as a reminder, today's Thursday. Please do the online quiz today, and then I've cut out yesterday's office hours because they're done and gone, but here are the rest of the office hours through the semester. If these times don't work, send me an email. I can't do this anymore. I gotta this costume. All right. Probably doesn't help that I'm trying to drink hot coffee. What role does Olaf the snowman have drinking hot coffee is another question altogether. And then final exam, just good reminder here that you got to choose your own 6-hour block of time on either May 12th or 13th. There are some practice materials for the exam that I'm still trying to finish up making. I should be posting them today. Okay, so what's the deal today? Most of the time in algebra, just to make the calculations go a little more smoothly, we tend to introduce a function as having one input variable and one output variable, and call it that. Y equals f of x, right? So we would do things like, just for small example, f of x equals x squared plus 1, and when x is equal to 5, you can plug in 5, you can plug in the input 5, and you could compute 5 squared plus 1, you get 26 as the output, right? So this y equals 26 is the output when x is 5. If you picked a different input, like 10, then you get an output of 101. Just as a note right now, sometimes people have the impression this is two functions. This is not two functions. This is two examples of input and output with one function. So this is the function. When you put in 5 as an input, you get 26 as an output. When you put in 10 as an input, you get 101 as an output. Okay, so most of the time in an algebra class, certainly through the entire semester, you just have functions with an input variable and an output variable. So like x is the input variable, y is the output variable. Reality doesn't really consist of functions of just an input variable and an output variable. More realistic would be the situation of a function with two input variables and an output variable. So in this next setup, I've got x and y are the input variables. So no, normally y is the output variable, but I needed x and then another letter. So x and y are the input variables, and so I guess the next letter z will be used as the output variable. And so to try to create the same kind of setup like y equals f of x, now in the setup we have down here, z equals f of x comma y. This looks a little strange, but like I think from an example you'll see like, okay, this is not so bad here. So f, here's my new function. This function f has two input variables x and y, and the formula for the output is 3x plus 4y. Just like over here, the formula for output was x squared plus 1. Now the formula for output is 3x plus 4y. So for example, to find f of 5 comma 10, we just the 5 here is before the comma, x is before the comma. We got to be careful about which thing we plug in for which. So plug in 5 for x, plug in 10 for y. So 3 times 5 plus 4 times 10 equals, and then I went ahead and simplified it all the way down to get the number 55. Okay, so I hope that doesn't look so bad for a first example of a function with two input variables. I have on the next slide several more examples of this idea going on. Functions with two input variables and one output variable. So here's another function with two input variables. So this is f of x comma y equals 3x plus y squared minus x to the fourth. So taking that function, let's find what f of 5 comma 6 is. So we should plug in a 5 for every x, and plug in a 6 for every y, right? And so we'll have 3 times 5 plus plug in, there's a y right here. We got to plug in, oh, come on, pen. We got to plug in 6 for the y. And so we have y squared, so 6 squared minus x to the fourth. So we've got to plug in, sorry, pen is having an issue there. There we go. Okay. We've got to plug in 5 for the x, so we have 5 to the fourth. I didn't bother simplifying the number this time, unlike the previous example we just looked at. But whatever number that would be in a calculator, that would be the output, right? So using, there's a kind of combination of inputs. So 5 is the x input, 6 is the y input, and then whatever number this is, we'll call that the z output. Okay. Here's another example. Another function with two input variables. So g of x comma y. So x is one input variable, y is the other input variable. The formula for the output here is 10x plus xy plus 5 times y squared times x. The square does not affect the 5. I wrote it a little funny here, just for emphasis of always read things using the order of operations. Oh, a little typo in my notes. That should be a g. I'd like to find g of 3 comma 1. So plugging in to this formula here, plugging in 3 for every x and 1 for every y, I believe looks like that. If I didn't make any other mistakes here. Yeah, 3 for every x, 1 for every y. Okay, and I'd say just leave it like that, right? But I wanted to make a point, so I simplified this down to 48. I also want to compute, and then sorry again for this, g of 1 comma 3. Now notice that I've swapped, there was a 3 first and a 1 next, and notice these are swapped. So I've got to, because of that, we need to make sure to plug in a 1 for every x now and a 3 for every y. It should look like this. So if you go back to this formula up here and plug in a 1 for every x and a 3 for every y, if you simplify that entirely, you'll get the number 58. The key thing here, just meaning, please be careful, right? So g of 3, 1 and g of 1, 3 don't end up being the same. You've got 48, you've got 58. So you just have to, be very methodical and just look at, the order of the variables listed here, and then the order of those numbers, and just follow that order, and everything should be okay. On this slide, I have an example of a function with three inputs as well. So this is new, but again, I don't think it'll be too bad. So you've got a function named h with input variables x, y, and z. Three input variables, and here's the formula for the output. So to find h of 10, 9, 8, we should plug in 10 for every x, plug in 9 for every y, plug in 8 for every z that we see. Boom, that number. Okay. So overall, I hope what this is looks okay. It may seem a little peculiar, but the work of just plugging in values, we've done in the past plug in x values into a function. That's very algebra-like, and I would call this the ideas that we're seeing here to be algebra. We're about to talk a little calculus related to this in a moment. I will say that again, like the previous slide said, that a function. Most of the time in calculus, and certainly all the time in algebra, the focus has been on functions with one input variable x and one output variable y. And I had hinted, or said at least, that a function that has two input variables, or now maybe three input variables, is more realistic. And what the hell do I even mean by more realistic? We're not gonna get too realistic. The more realistic you get, the more complicated the calculations become. So I don't want to overdo it, but I want to just talk about it just briefly, right? So while y equals f of x, which we've done kind of most of the time, keeps calculations easier, z equals f of xy, it's more realistic. It's more like reality, right? So in real life, a quantity, let's just say z, it doesn't usually depend on two quantities either, actually, right? Like more realistically, a quantity that people actually want to keep track of relies on many other quantities. So for instance, just to make a small example, right? Like if z represented the profit of a small restaurant, I mean just like a mom and pop shop, right? Like then z would depend on many quantities, like many other numbers, right? So like for instance, one of the numbers might be the number of employees that are hired in a year, or the pay rate of the cooks, the hourly pay rate of the cooks, or the pay rate of the wait staff, the cost of lettuce, and that will change seasonally. How many customers visit in a typical evening, right? Average number of customers in an evening. How many freebies that the restaurant gives out? Like so many things. Like all of these things have numbers attached to them, and all of these you could talk about how all of these things should have some kind of effect on the profit of a company, right? I mean, and then there's many other things missing. I've never run a restaurant, but there's probably a lot of other quantities that are actually more relevant. Some of these probably have less of an effect, like the number of freebies given out. If it's not too many, probably doesn't have a huge effect on the profit of a restaurant. But like all of these things would affect the profit, right? Like you give out freebies and your profit kind of automatically goes down because like the house paid for it. So, we've kept as much as possible this view of a function should have one input variable and one output variable, but the kinds of functions that people really want to do optimization on, for instance, have many input variables. Even a tiny little restaurant would have a function with many input variables. And so what are we going to do with this? What's the calculus behind what we're going to do? Is today we're going to talk about a modified form of the derivative. And what I mean by that is so I just took that sort of block set of statements at the bottom of the previous slide and said, what we're going to do for right now is we should talk about how a restaurant's profit would change if all of these quantities below, just stick with these ones right now, if they all remain constant. So like each of these has a number associated to it. Let's just say, to keep it easier to think about, there's the number of employees hired per year. Let's say that this is a small restaurant. They hire 2 employees per year because they lose 2 employees per year or something, right? So let's just keep it at 2. Don't change the number. The pay rate of the cooks, let's say that remains constant or whatever. So all of the quantities remain constant with the exception of one quantity changing. Just to keep track of things, just one of these numbers is going to change. Which one? The one in red. So let's just say the pay rate of the cooks remains the same. The pay rate of the waitstaff remains the same. The cost of lettuce doesn't change all year long. That's unrealistic, but let's just pretend for a moment so we can talk about a computation. All of these other things that are not highlighted in red stay exactly the same, but the number of employees hired per year is to change. So instead of hiring 2 employees per year, this restaurant wants to consider hiring another, like 3 employees per year instead of 2 employees per year. Or let's go back, highlight a new quantity in red. Let's say the restaurant's like, no, no, we know we couldn't afford hiring a third employee per year, so we're going to stick with 2 employees hired per year. But we want to talk about the cooks. They've done a good job, and we want to give them a raise. Like, how's that going to affect our profit? And think about it, right? Like, it's the right thing to do to give them a raise if they haven't had one in a long time. But if the pay rate of the cooks goes up, the profit of the company has to go down, right? Unless something else changes as well. If you just start paying some employees more than you used to, then that cuts into the profit. That can still probably be done, but it's just like this is what we're trying to do is we're trying to talk about detecting this change. So same deal, like the cost of lettuce. If the cost of lettuce goes up, then that's going to probably lower the profits a little bit. And the more the cost of lettuce goes up, the more the profits are cut into. Versus this one, how many customers visit in a typical evening? So let's say you normally, it's a small place, and you over the course of several hours in an evening you get maybe 50 customers, I don't know, and then you have a good day. Maybe somebody had a birthday thing and huge bash, and they just invited lots of people, so instead of your typical 50 in an evening, you had 100 people. So if the number of customers goes up, and let's say it goes up every evening for many evenings, then that's going to probably mean something really good for the profit of the restaurant, right? Because they don't have to throw out as many things that go bad that they just had to stock up on or whatever, right? So like all of these things should have some kind of effect on the profit. And to keep track of things, the mindset we're going to have in what we're doing is, what if you kept all of these quantities constant with the exception of one? You just allow one of these to change and then talk about how does that affect the profit. And so this change, we talked about the derivative being change. The derivative is a slope, right? And slope is a rate, and that is rate of change. So this is what we're going to do using this thing called a partial derivative. So how does this work? We'll see a computation on the next slide, but the idea is just basically to keep all of those input variables constant except one variable. All variables constant except one, and then take a derivative. There are 2 notations for it that I want to introduce. So if the variable x is changing, one of the notations is f and then a tiny little subscript x. This is a lot like the f prime notation. And then over here, it might be a little too small, so I'm going to just write this over here. So looks like that. This is a lot like our earlier df over dx notation. It's just for partial derivatives. For one reason or another, the d's kind of become a little curlier shaped, but it's other than that, it means the same. So then, same deal. If you want to keep track of how does the output change, as just the input variable y changes, but the other variables are kept constant, then here's your notations for this. This looks all a little much, but like we'll just, if we dig into an example, I think it'll be okay. So I want to look at this function f of 2 input variables x, y, and the output is given by 3x to the 5th y squared plus y times ln of x plus y to the x. So think of this like this formula here is going to give the profit of a restaurant. Again, it's not realistic enough. Like realistic would be like there'd be more than 2 input variables. There'd be 10 input variables or 20 input variables, but we don't want to go there, right? So we're just going to go with 2 input variables, and this is the profit. And here this says find f sub x. So this is that partial derivative, meaning we're going to treat x as the variable and treat y as a constant. So like maybe x represents, kind of going back to that list, the price of lettuce, right? From like, and y represents the number of employees hired in a year. And so we want to know how does the profit change as the price of lettuce changes. Right? To do this, the number y, which is just again just to make up Oh no, no, no! Don't close that. So we're going to keep the number of employees constant, right? Keep y constant. Pretend y is a constant, even though it's a variable up here. We're just going to pretend it's a constant, and then take the derivative. And in fact, this is what the warm up was about. So to pretend y is a constant, I'm actually this is again, I'm just making up some things here. Like this is just to help argue a point. Okay, so we pretend y is a constant. Now this work here, it should not be actually part of the answer. Okay, but I'm including this here because I think it helps us think about what's going on. So if we pretended y is a constant and even picked for just for a moment temporarily a specific constant 10, then this should become 3 times x to the 5th times, and then if y is really 10, y squared, 100, plus y ln of x. I'm plugging in 10 for y right now, 10 ln of x, plus y to the x, plugging in 10, we have 10 to the x. This was actually the warm-up. Right? The warm-up said, given this function, differentiate it. In the warm-up, this was called f of x, and you were asked to find f prime of x. Well, going back to how we did that warm-up, we had this, this is a product with 3 things, but just as a reminder, 2 of those 3 things here are constants, so those were copied. Right? No need to use the product rule when most of the pieces are constants. If just one piece is it has the variable, just that part needs to be differentiated. So x to the 5th was differentiated using the power rule to 5x to the 4th. 10 times ln of x, copy the 10, differentiate ln of x, 1 over x. 10 to the x, just a reminder, the derivative of an exponential function is base raised to that exponent times ln of that base. So this is this warm-up was helpful, and I hope very relevant to keeping track of what we need to do here. And in fact, just because this is our first time around, I tend to skip this step in the future, but like I think it's good right now just to go like, okay, if we're really pretending y is a constant, let's just take 3 and the y squared. Those are all constant, right? If y is a constant, again, we don't really know what constant. I just was pretending that y is the constant 10. But if y is 10, then y squared. If y is a constant, then y squared is a constant. For example, if y equals 10, then y squared is 100, a constant. And then 3 times a constant is also constant. So all this stuff in parentheses, 3 times y squared, we're pretending that's a constant. We don't know what constant because we don't really technically know what y is. So we're going to call that part a constant. And then, so then if we were to differentiate, again, we don't know what number this is, but circled right there, we're pretending that's a number. Then to take the derivative, another typo, sorry, I'll get this fixed. To take the derivative, we copy that constant, this constant is copied, and then you differentiate x to the 5th. That derivative is 5x to the 4th. Copy the constant y here. Again, we're treating y like a constant, and then differentiate ln of x, and you get 1 over x. Over here, y to the x. Treat y like a constant. So taking the derivative of y to the x, if y is a constant, is just like what we did here. Taking the derivative of 10 to the x. I want you to view the 10 to the x and the y to the x in very much the same way. And just like the 10 to the x, its derivative over here was 10 to the x ln of 10. The derivative of y to the x over here is y to the x ln of y. So notice that everywhere there was a 10 in the warm-up, there's a y instead in this question. We're going to pause, see how we're doing, because this is a little funky at first. Once you get used to it, it's not bad, but it's a little strange at first. Okay, we're just going to look at more examples. This is the only thing for the rest of class today, really, is so what's going on here is if you're given a function with 2 input variables, to find f sub x, you treat y like a constant. I should just comment that this is not the same as ignoring y. Sometimes that's what people understand I'm trying to say, but I'm not saying ignore y. I've seen people like take the problem and just like basically erase all the y's, but it's not that. You instead treat y like it is a constant and then differentiate using the usual derivative rules. So let's look at another example. So okay, so I've got z is the output variable. The function here has two input variables, x and y. We've got here 10x squared minus 4x squared y plus 12y plus 3x times y to the second plus 6. I'd like to find the partial derivative with respect to x. So we're going to treat x like the variable, treat y like a constant. Another way to write this using the other notation would be this funky looking dz over dx. Again, there's just two notations. This f sub x is usually less writing, so okay. And again, because we're treating y like a constant, if you like, it is helpful to think of putting constants in front. So just like this 10 is in front of the function x squared, that 10 is okay. And then over here, just juggle the order. Well, 4 is a constant, y we're treating as a constant, so 4 times y is a constant. So just stick this all together in parentheses. If it's helpful, convenient to you to think of it this way. 12y, that whole thing is a constant, right? If y is a constant, 12 times y is a constant. And in fact, 12 times y plus 6 is a constant. So I just put all of, like what's in parentheses here, we're treating that whole thing like it's a constant. If y is a constant, we don't know what constant. I mean, we just pretend for a moment, just like we did the last problem, that y is 10. Then 12 times y would be the constant 120, right? So we're treating this like a constant. And then same deal here. This 3 times x times y squared. If y is a constant, then y squared is a constant, and 3y squared is a constant. So I've got here constant times variable. Again, you don't have to do a step that looks like this, but I think sometimes you'll find it easier to process by writing like this. And so then now to find the partial derivative. So this is like the prime notation, right? In the past we would have had f prime, but there is just a slight different notation. But instead of putting a thing up here, there's a thing down there for the partial derivative. So take the derivative of 10x squared, that part, okay, 20x to the first. The next part, let's talk through a little more though. So copy the minus sign. 4y is a constant. Well, remember, if we're treating y like a constant, then 4y is a constant. 4 times y is also a constant. So copy the constant and then differentiate x squared. That derivative would be 2x using the power rule. This part, let's talk about 12 times y plus 6. That whole thing in parentheses is a constant. If y is a constant, we don't know what constant. Like somebody has hidden what number y is, but if y is just a number, then 12 times y plus 6, that whole thing is a constant. So the derivative of this constant is 0. And then over here, 3y squared times x. Copy the constant 3y squared, differentiate x, the derivative of x is 1. Let's just pause and see how we're doing with this. Okay, I'd like to actually take the same function and do one other thing. So we're done with this question, but using the same function, let's see here. So same function, f of xy is same function. I'm going to just change how the question looks. So we're going to look at the partial derivative with respect to y now. So because this tiny little subscripted y here means we're going to treat y like the variable, and therefore all other variables, and the only other variable in this example is x, we're going to treat x like a constant. So every time you see an x, pretend that x is like a number, like pretend x is like the number 9 or the number 900 or whatever, right? So x is a constant, y is a variable. So to find the partial derivative with respect to y, 10x squared, that whole thing is a constant, right? Remember, right now because y is the variable, we're treating x like a constant. So 10x to the second, that entire thing is a constant, the derivative is 0. Copy the minus sign right there. 4x squared y, well, again, I didn't draw in all the parentheses, but this 4x squared part, that whole thing is a constant. So copy the constant, 4x squared. And then the derivative of y is 1. So I just didn't write in a times 1, though I could have. The derivative of the variable y is 1. 12 times y, copy the 12. The derivative of y again is 1, so there's a times 1 here if you really want. 3x is remember x is a constant, so 3x is a constant. This is like this coefficient in front for the constant multiple property. Copy that constant 3x and then differentiate y squared. The derivative of y squared is 2y. 6 is definitely a constant, and then its derivative is 0. So maybe all this marking makes it a little harder to read. So it took the same function as in the previous question. If we treat x as a variable and treat y like a constant and differentiate, you get this. If you treat y like the variable and treat x as if it were a constant, then the derivative would be that. Just seeing how we're doing. See if. Okay, and then as a very minor follow up here, we're going to use the same function again as in the previous two questions, and now this says find f sub x of 1, 5 and find f sub y of 1, 5. So we've done the hard work up here. Now we're going to do a much easier thing of just some algebra. Now that we have the partial derivative and the other partial derivative. Oh, that's the thing. There are two partial derivatives because there's two variables, two input variables. So now that we have this partial derivative function, now we take that partial derivative function and plug in 1, 5. That's all, right? So it took what's up here, f sub x of xy, and plugged in 1 and 5 for 1 for every x, 5 for every y. So I just took this, pasted that here, replaced every x with a 1, replaced every y with a 5. The other half of this was to find f sub y of 1, 5. So I took this, put it down here, just replacing every x with a 1 and every y with a 5. Again, I know this is a little strange at first. It takes just a little getting used to, and then it's usually not too bad. But think about this like, one of the numbers that the restaurant has control over, they're like saying, let's not change it, but let's consider the possibility of changing the other. Or maybe they don't even have control over it. Like, what's going to be the effect on our profit if the price of lettuce goes up? All other things equal, just what happens to our profit if one number changes. So let's I should just, regarding this follow-up question, comment and say what is this trying to do. So I actually took just to talk about it, not that I would expect a number like this to ever be simplified. I did have this 38 so I can talk about what this is about. So this is trying to say that as x changes from 5, so x starts at 5, but it's going to change. X is going to increase a little bit, but the other variable x. So yeah, if y changes from 5 to, and the y value is going to grow, but the x value remains 1. Again, we're not changing it. Then z, the output, changes by 38. So a tiny change in a 1 unit change in y starting at 5, y growing from 5 to 6 is going to make the z value, the output of this function, change by 38. So in this example, whatever y represents, when y grows, the profit grows by $38, something like this, right? That would be the interpretation. I should also comment that in the past, what we did was, and this is not that this is false anymore. sorry for how I'm wording this. I'm saying we had a function, then you had to find the derivative first, and then if you needed, because maybe the question required it, you had to plug in your x value after you found your derivative. If you plug in the x value before, then you'd have a constant, and when you differentiate, you just have 0, right? So you had to take your function, differentiate, then plug in your x value. And in the same manner here, if you're given a function with 2 input variables, you should find your partial derivative first, and then you plug in your input values. So I have this example that I'd like to talk through. So I've got function f of xy equals 3x to the 10th y plus 2x to the 5th y to the 7th plus 8 times x times y to the 8th. And find partial derivative with respect to variable x, find partial derivative with respect to variable y, and then only after we do those things we'll plug in 12 and 9. So, for example, just as a reiteration of that point that was just made, we got to not plug in the 12, 9 yet, not yet, because if we do, we'll just have a constant. So here, to find the partial derivative with respect to x, we treat y like it's a constant. So if y is a constant, I just took that 3y and I just wrote it first. Then x to the 10th differentiates to 10x to the 9th. Over here as well, if y is a constant, y to the 7th it should be thought of as a constant. If we think of y as a constant, y to the 7th is a constant, 2 times y to the 7th is a constant, all that constant is just stuck in front. And then differentiate x to the 5th and you have 5x to the 4th. Same deal here. If y is a constant, then 8 times y to the 8th, that whole bit is a constant. The leftover piece x differentiates to 1. Now that this is the partial derivative function with respect to the variable x, and then we can plug in the 12 and the 9 up there. 12 plugged in for every x, 9 plugged in for every y. It should look like that. Okay, so that answers this part. Then we need to look at the partial derivative with respect to y. So go back to the original function up here. Now we're treating x like it's a constant. Every time we see x, we pretend it's a constant. And so this 3x to the 10th, that whole thing is a constant, so we copy that. However, this variable y differentiates to a 1. Over here in the next term, 2x to the 5th, that portion here is treated as a constant, so we copy the constant using the constant multiple property. And then y to the 7th is differentiated as 7y to the 6th using the power rule. Over here, if x is a constant, then 8 times x is a constant, so 8x is copied. And then y to the 8th is differentiated using the power rule. You have 8y to the 7th. Okay, so that's the other partial derivative function, and then we plug into that partial derivative function. We plug in the 12 and 9 and get a thing that looks like this. Okay, I have another example. This function is x times square root of 6x plus y. If you find it more convenient, you may wish to think of this function as x times 6x plus y raised to the 1/2. That's kind of how I've been thinking of it. So find the partial derivative with respect to x and the partial derivative with respect to y. So how do you find f sub x? You pretend y is a constant. So in fact, just to illustrate a point, I think because of how some of these build up, it might be nicer to just some like separate but related question. I just pretend y is really a constant by plugging in something for y. Not that we really should when answering this question. This is like a scratch work thought off to the side. But if y is a constant, I just picked a constant. I just picked the number 1,000. And just to name it different, because I didn't want it to be confusing with what we have up here, I just named a new function. This function only has one input variable called x. And so if we just place a 1,000 in for where y is, I ask myself, staring at this, how would I find the derivative of g? Right? So g only has one variable, so that's why I wrote the prime notation. How would I find the derivative here? I'd have to use the product rule, right? Because both of the pieces, both this piece and that piece, have the variable. So noticing that that has to be done using the product rule, that tells you that if you go back to this original thing up here, the derivative is going to use the product rule as well. That's the great thing about these. If you're like, which derivative rule do I use? Just temporarily off to the side, plug in a number for the variable that you're not differentiating with respect to, and then however you differentiate this function, whatever derivative rule would technically apply here, that's the one that's going to apply up here. It just works out exactly that way all the time. So here we go. Product rule. First times the derivative of the second. So copy the x. Again, I'm thinking of this next part as a 6x plus y raised to the 1/2. So the derivative of that, treating y like a constant, requires the chain rule, right? So in fact, I'm missing my 1/2 here. So 1/2 then the inside thing, 6x plus y raised to the negative 1/2. The chain rule says you need to differentiate 6x plus y. So 6x differentiates to 6, but y is a constant. The derivative of y is, if y is a constant, then the derivative of that constant y is a 0. You don't have to write the plus 0, but I thought it's helpful right now for emphasis. And then the second half of the product rule is you take the second part, so 6x plus y raised to the 1/2, that's copied, and then you need to differentiate the first part. So the x needs to differentiate, and you get a 1. Okay. How do you find, oh my goodness, how did this happen? This should be f sub y. How do we find the partial derivative with respect to y? Now we need to pretend that x is constant. So just to really like be able to think about that again, I just plugged in a number for x. I just went back up here. And this is not something we should really do in showing our work. It's just a little thing to do off to the side so that we can go like, oh yeah, what derivative rule should we use? So I went ahead and picked a number for x. I just picked 99. And so if you do that, you have what? 99 root x, so 6 times, and then plugged in just temporarily 99 for x. And so I asked myself, how should this be differentiated? You don't need to use a product rule for this one because the variable doesn't appear in both pieces. This would be like copy the number 99 using the constant multiple rule and then differentiate this next part using the chain rule, right? So oh my goodness. Okay, I'm gonna. So how would we differentiate this? We're just gonna work this out because I don't know why the 99's in there. So f sub y. I'm going to obviously post a corrected version of this. Sorry about this, folks. So we treat x like a constant up here, then copy x. Just like over here, if there was a 99 here, we would just copy that constant when differentiating this. So copy x is x. I know it looks like a variable, but we're treating it like it's a constant. And then to differentiate this next part using the chain rule, we'll have times 1/2. The inside stuff, so 6x plus y raised to the negative 1/2 times, remember the chain rule requires the derivative of the inside stuff. Now when you differentiate 6x, so the inside stuff is 6x plus y, but when you differentiate 6x, remember we're treating x like it's a constant, so 6x is a constant and the derivative of 6x is 0. There is a y. Y is the variable right now, and when you differentiate y, you get 1. Ooh, sorry about that mess. Okay, and then the when finding f sub x, you should treat y like it's a constant. Don't ignore y. That's kind of what sometimes people hear. I should ignore the variable, but that's not actually what's happening. So like here's a small example that I think helps illustrate this point. So let's just look at a function where the rule for the function is x to the y power. And then I'd like to just find the partial derivative with respect to x and the partial derivative with respect to y. So partial derivative with respect to x. So we treat x like x is the variable, treat y like y is a constant. And so x to the constant, right? Like think of how you differentiate x to the 5th, for instance. It should be using the power rule. So same deal, right? So here, the derivative using the power rule, you take the exponent y and you bring it in front and you lower the exponent by 1. However, if we look at f sub y, now we treat y like the variable, treat x like the constant. And if x is the constant, so constant as the base, variable as the exponent, then to take the derivative, you should use the exponential rule. Sorry, I keep trying to cross out the things that are erroneous up there so that so then the derivative here, if you know base x of not a variable right now, we're treating it like a constant raised to a variable, that derivative is you copy that and then time, remembering how the exponential rule goes, times ln of whatever that base was. So this is the same deal as when you differentiate 3 to the y, it's 3 to the y times ln of 3. So the derivative of x to the y, if x is just pretend x is a number, then you have x to the y times ln of x. Okay, we'll do one last example here. Oh, yeah, sorry about this. Okay, so what about if sometimes I think actually it's oddly enough easier to spot what's going on if we look at functions with not 2 input variables as we've been doing so far, but rather 3 input variables. So with 3 input variables, x, y, and z, let's look at this function x squared times y to the fourth times z to the sixth and find f sub x, f sub y, and f sub z. Okay, so to find f sub x, right, which we'll treat x like a variable, treat y and z like constants. And so when you differentiate this, if y and z are constants, this whole block here, y to the fourth, z to the sixth, that's all constant. And in fact, I just copied those in place. I didn't shuffle the order. I could have shuffled the order. I just copied the constants and then differentiate x to the second, and that derivative is 2x, right? The derivative of x squared is 2x. When you have a function like that part multiplied by constants, those are considered constants right now. You differentiate the function part and you copy the constants. Same general deal for f sub y. So to find f sub y, y is now the variable. In this problem, y is the variable now in this portion, right, for this part. Y is the variable. X and z are treated as constants. So I copied the x squared constant. I differentiated y to the fourth as 4y to the third. And then copied z to the sixth, because z to the sixth is a if z, right now we're treating z as a constant, therefore z to the sixth is also a constant. For this third part, partial derivative with respect to z, now z is treated as a variable, x and y are treated as constants. So we can copy the x squared and y to the fourth parts and just differentiate, because these parts are the constant, and just differentiate z to the sixth. And so that derivative should be x to the second, y to the fourth. Those were copied. Those were considered constant right now. This z to the sixth part is differentiated, and we get 6z to the fifth. Okay, so just some reminders. Today, Thursday, so please complete the online quiz. Here's a listing of office hours. If these times don't work, please feel free to send me an email and we will find another time to meet. This has been the offer all semester that if times don't work, we can set up a time to meet at some other time. Choose your own 6-hour block on either Tuesday, May 12th or Wednesday, May 13th in which to complete the final exam. And send up more details about the final. I think I've gone over some of these before. Yeah, so there's within that 48-hour block of time, you're choosing a 6-hour block of time. I'd like you to please turn in a single PDF file that has all the questions answered in order. Please show your work, practice problems, and information about the exam, and so all that will be posted in PDF format in Canvas. And I would keep current with web work. So the last web work should have been started yesterday. That would be ideal. Although WebWorks 43 and 44 are both due Monday, May 8th. Therefore, I decided to count them as extra credit assignments. And then just as a final word, I want to say thank you for your participation and understanding through the process. It's been quite a wild ride. I'm sorry, not for anything specific I've done, but what I mean is just, yeah, so sorry that this had to be your experience of the rest of the semester. Take care of yourselves. I miss the interaction as much as I like the idea of teaching math, and that is very fun for me. Don't get me wrong. Like I think the bigger thing is just being able to like talk to students who want to give up on a class or like or just whatever's going on in life, like being able to talk about those things. That's what I really miss the most. And I recognize that there's a lot of stresses that you might be living in a challenging living situation, or know somebody who's sick, finances, work schedule. I realize that there's a lot that's going on. So, yeah, just I'm thinking about you and sending positive thoughts. I think since this is applied calculus and we didn't get to do even quite as many applications as I want. I think I should just it's very relevant. And I think I should say this for an end of the semester for this class is to say that I think sometimes some of the applications of calculus don't feel relevant all the time, and I recognize that. But I am trying to cover the things that CBA, which is the vast majority of students enrolled in 175, that the faculty there have asked for. But that said, let's think about some realistic, in light of recent situations. When I think of like the number of newly infected people with this disease, per day, I wish this were a decreasing function, right? Like it's not like I'm watching the news and always trying to put on my math hat with this, but like I think I think that calculus gives us some good language to talk about some of these things. I really want the first derivative to be negative. That would be great, right? But like that's not happening currently. If at least last I checked in the U.S. However, if there were no choice, like if f had to be increasing, if the first derivative had to be positive, then I'd want the second derivative to be negative, right? I mean, like if you had to have increasing, do you want that for the number of infections? Do you want that? I want concave down. If it had to be increasing, I want concave down. In this language of flattening the curve, I think that's what people are trying to go for. They don't want to talk about concavity because that's not language that people use. And then it's really maybe a separate note, but like minimizing the number of fatalities, it's a realistic optimization problem, and that's people are epidemiologists. I actually do have some friends who are in the area. Think of using calculus and think about a situation like what we've been looking at here, functions with multiple variables more than just an x variable, and think about some kind of concept of take a derivative set equal to 0. There's a version of that for partial derivatives. We are not going into this clearly, but like that's realistic application of calculus. If you need anything, whether it's math related or not, please feel free to reach out even after the semester ends. Yeah, take care of yourselves. Thanks.